Welcome to my fast little snippet of kind of what this project is about. I'm going to try to keep it around the guidelines of the project, which is about 5 minutes. But anyway, I can kind of get right into kind of what my project is about. So basically, I wanted to do something that was interesting to me, and one of the biggest things for me was weather. I love weather. I'm a total geek about it. I love, watching it. I love learning more about it, how weather develops. So I wanted to do kind of something in that range. So I looked at some of the websites where you can get data sets, and one of them was Kaggle, and I was able to find a U.S. tornado data set from the 1950s to 2021s, which lists every single tornado that has happened, as well as tons and tons of other inputs. And so I just wanted to talk about my main question, which is can a neural network predict if a tornado caused casualties based on intensity, size, location, and timing, magnitude, as well as some other stuff that we'll talk about later. So at the very beginning, I obviously read in my tornado.scv, and then I was able to kind of basically clean up the data a little bit. And this kind of talks about it. So you got year, month, day, date, magnitude, if there were any injuries, as well as length, width, and these are just some longitudes and latitudes. And I do get rid of those because those aren't very important. It's important to know that I used, I think it's up here, binary classification. So a 1 is a casualty and a 0 means there's none. Casualty means injuries or deaths. So if there was one injury, there would be a casualty with a tornado, etc., etc. Um, so down here, this is kind of a fast little image of the distribution. Sorry, I can't talk. And you can see the number of tornadoes. About 60,000 tornadoes were had no casualties, which is honestly insane. And then only even less than 10,000 had one. So that was one of the big things of is basically it is heavily skewed. You're not going to see as many strong tornadoes as you are going to see weaker. So that was something to keep in count, basically for us the count of the project. Also, I had to get rid of -9 because magnitude is kind of like the EF scale from 0 to 5. If there was a -9, that means it was unranked. So I had to get rid of those. This is distribution by year, distribution month. So you can kind of see how heavily skewed, width, how heavily skewed all this data is by just using all those charts. But anyway, I can go down to phase 2 because I'm running out of time. So this is predicting without machine learning. So I wanted to kind of map everything out, like with these, and then I tried using a rule-based tornado predictor. So I manually typed this stuff in. So I made a square 0, 0, and so in my head, magnitude, length, and width are going to be the biggest ones, most likely for a violent tornado to affect people. So I just added like if the magnitude was above or equal to 1, I would add a square of 0.15, and so on. So if it was a 3, it would do 0.15, 0.2 plus 0.25. So it would be really high. Length and width were the same. And so if the score was above a 1, obviously it would be a 1.0. But also, these were the scores. So, the magnitude 3, length 3.6, width the 130, casualty 1, the real score had a 0.65, which is not bad. But I was able to change it where if it was a 0.5 or above, it would only go to a 1. So let me see if I can go down to the accuracy, sorry. So yeah, precision was honestly not too bad, 0.478, and the recall was 0.44. This kind of shows the real base scores of everything. And let's go to phase 3. This isn't as important as directed in the notes, but basically I had to make neural networks that would overfit the data set, and the data set is giant. So I was able to split it, However, it took a while. I actually had to make it smaller. I'm pretty sure in order for me to fit everything in. Yeah, I had to literally make them smaller because it took a long time on my computer in order to build. Um, all this code, I tried creating it first, and then I won't lie, it was kind of difficult to kind of try to understand all of it. So I did have some help with Google and stuff like that. But you can kind of see the accuracies of kind of what it is. But for me, the most important thing was focusing on the F1 score. To keep going, it's running out of time. But phase four, this is when it gets more important to kind of figure out. So I had to select a model that was the best, basically. And let's see if I go down to where, yeah, here are my functions, because those are very important. My large neural networks. I made singular, small, medium, and a large network as directed by the project. And these are all the data sets. So specifically looking at the F1 scale, the F1 score, because the data is so heavily skewed, you can see that the single neuron actually had a 0.41, which is pretty good, but the large network had a 0.45. I wanted to make the networks larger. However, just because of computer limitations, it just took forever. I think when I first tried running my code, I left it on for like an hour and it still didn't even finish. So I did have to adjust it. So I wish these could be higher, but 0.45 is not too bad. And then yeah, these are just ascending. So large neural network was the best. It had the best validation score as well as the best recall and accuracy as well. And then these are just kind of the learning network curves, so the accuracy over time. And then these are the same as well, of just like small, single, large. Kind of see the training loss and validation loss drastically goes down to 0.25. But the best was phase four for sure. Let's see. Yeah, best model was a large network, neural network, with 64, 32, and 16 layers. And the recall F1 was 0.45, kind of like we talked about. This is kind of going over random stuff at this point. So let's see. Let's go into phase five because I am completely out of time. So the main goal of this was to figure out if I was able to train a neural network, getting rid of certain inputs and determining which inputs were the most important. So let's just go on. So one at a time, I trained on year, month, magnitude, length, with all that stuff. And these were the top ones. So magnitude was the number one, was a 0.38 f1. Length and width were top, but everything else is very low. Like wasn't as important. And this is another graph of how important magnitude, length, and width was compared to everything else, all the other inputs. This isn't as important. Just validation accuracy as well for a single feature model performance by validation accuracy. So I wanted to figure out kind of like this feature removal order from least important to most important. These were the least important and these were the most important. So the goal was to basically every single time I would remove one input and then I would redo the neural network. I would make it relearn everything. And what I determined was after every single time, starting at none with 454, I removed year, month, SLON, starting latitude, year, month, starting longitude, starting latitude, ending latitude, all that stuff until eventually I removed, I think this is 8 or 9 features. But you can see that every single time we remove a feature, the F1 score goes down, especially after we remove some of the more important ones, it drastically goes down. That being said, yeah, this is the validation accuracy after every feature removal. That being said, the best model, I wish it was one of the ones we just did, but no, it's actually having all 9 inputs, and that could just be because of um like year, month, days, those can be important, where it starts and where it ends as well. Maybe the neural network is able to pick up on things that are not there. But yeah, hopefully I didn't go too over the time limit of this video. If so, I'll need to submit. But yeah, thank you for listening to me.